doing it as well. So take it away. Thank you.
Thank you very much. I'd like to start by thanking Dom and Christos and the organisers for the invitation to speak to you today. So I'm a methodologist, and I was invited to speak today to provide a somewhat sceptical perspective, which I'm quite glad to do. It was largely on the basis of this paper by Richard Dinger, which was he's a postdoc in my group at the Dondas, where he replicated or attempted to replicate the very high-profile study in depression. Now, I'm not really going to talk about that today. I'm only going to come back to it in passing a couple of times. I would refer you to the Replication Award poster to go and have a discussion about that in detail if you'd like to. What I would like to do is to lift the discussion today into a little bit more of a conceptual level and talk about some general principles that I think are applicable to many studies. So I'll talk about three things. I'll talk about the use of clustering methods in psychiatry for subtyping cohorts. I'd like to raise awareness of a few caveats to that approach and close with some methodological recommendations that might be useful in many studies. So if you were interested in subtyping clinical cohorts, you might start with a perspective like this. I've chosen the RDoC perspective, but that's not really particularly important. The conceptual idea is the same. And essentially the idea would be that we have these heterogeneous behaviorally diagnosed disorder groups. So for example, depression, schizophrenia, and autism. We might aggregate the data in a cross-diagnostic fashion. And then based on biology, symptoms, and other kinds of measures, the idea would be that we then arrive at subtypes that are more related to the underlying biology than what we had at the beginning. And just to read this out, it would be to develop for research purposes new ways of classifying disorders based on behavioural dimensions and neurobiology. Now, I would like to argue that there's a lot of this is not really new. So one of the things that we did recently is we reviewed the literature looking at approaches for subtyping psychiatric disorders. And clustering approaches like this have been applied since at least the 1970s. There are hundreds of studies, and I'd like to argue that for any disorder that you consider, we've still not converged on a consistent set of subtypes. That's not to say that frameworks such as RDoC have an added value. Of course they have, in terms of things like the careful characterization of behavior across different levels in conceptualizing the RDoC matrix. What it doesn't specify, however, is how we move from biology to clusters. That's just simply not specified as part of the framework, and that's really what I would like to talk about for the rest of the talk. So I'd like to, first of all, encourage you to think about, what are we aiming to do with this kind of approach? Are we really trying to find real biological subtypes in the sense of oncology that really map onto different proteins or different biological mechanisms? Do we want to explain variation across the cohort, or do we want to make better predictions of outcome? And those things have different consequences in terms of the level of validation that we would consider acceptable. And I'll come back to that later on. The first caveat that I would like to introduce is this one, that when we're talking about unsupervised learning, there's no universal measure of success. And I'd like to motivate that by this quote from Hastie, Tibshirani, and Friedman from their, in my mind, quite influential and authoritative text. And they said, in the context of unsupervised learning, there is no direct measure of success. One must resort to heuristic arguments not only for motivating the algorithms, but for judgments as to the quality of the results. This uncomfortable situation has led to heavy proliferation of proposed methods, since effectiveness is a matter of opinion and cannot be verified directly. And I'll contrast that with something like supervised learning, which is some of the examples that Paula talked about in the beginning, where we know that if we can predict accurately on unseen data, then we have a reasonable measure of how well we're doing. So to illustrate that, this is a fairly well-known example. So there are many different methods that one could choose to choose the optimal model order, for example, for different clustering algorithms. We could take a silhouette index, we could take a cluster dendrogram, information criteria, or reproducibility. Now, these may give us different answers, and they're all relative. So one of the first things I'd like to argue is that if we get a high score on one of these clusters, it doesn't imply that the clusters are real in any sense. And I'm going to illustrate with the following example. Supposing that we take reproducibility as our metric, and we take a continuous model derived from a Gaussian distribution, and lots of times we train, say, a k-means clustering algorithm on this continuous model, we get cluster centers that are very reliable, and we can reproduce them consistently. But it's clear that there are no clusters in this data set. That is problematic because clustering algorithms always give a result. So if I train a clustering algorithm derived on some data from this generative model, it's going to give, say I ask k-means to give me 4 clusters, it's going to give me 4 clusters. And again, if I sample lots of different data sets from the same generative model, I train the clustering algorithm again, I get 4 clusters every time. And there's some uncertainty, as you can see, with the particular clusters that I arrive at, that we should take into account as well. The point is that I would argue that we need to test against the null hypothesis that there are actually clusters in the data at all. And so this was something that Richard did in his paper to look at doing a similar procedure to what I've just described, building up a null distribution which represents the null hypothesis that there are no data in the cluster at all, then testing the chosen statistic against this null distribution. So that was something that I think should be more widely used in this kind of context. So that's this is a schematic that I often like to use to explain some of the problems that we encounter in psychiatric disorders. So I think most of us here would agree that the very clean case control comparison that I'm showing at the top left is unrealistic, and that's also spoken to by the data that Paula has presented. The default approach to that problem is to try to partition the clinical group into subtypes, and that is problematic for the reasons that I've just described. If we think about what might be happening at the level of the underlying biology, there are many other possible scenarios. So, for example, we could have something like a spectrum of functioning, or more likely, we have a convergence of multiple pathophysiological mechanisms on the same clinical phenotype, which is the most likely scenario in a psychiatric population. So I would like to talk a little bit about validation. So validation is really, because we're using these unsupervised techniques, it's absolutely essential if we want to demonstrate that these kind of clusters are meaningful. And I like to think of it in a hierarchical sense. So if we have something like a discovery and a validation cohort, by far the most, if you look at what's happening in the literature, by far the most common approach is to simply use the same cohort and the same measures for example, training a classifier on the clusters derived from a given cohort. Now, it should be clear that this doesn't provide any validation whatsoever. So we can say things like, how separable are the clusters, which variables are relevant, but in terms of how stable they are, it doesn't have anything to say. So what we could do, we could take that a step further, and we could say, well, let's take a new cohort with the same or similar measures, for example, some different symptom scales that measure the same thing in a slightly different way. And that's taking us a little bit further towards being able to say something meaningful. We can say things like, are they stable? Are they generalizable to the same population? So this is, of course, a different question to something like generalizing to a different disorder. We can take this further and we can say, well, let's apply it to a different cohort. So with a different clinical phenotype, for example, different measures, can we explain, for example, using clusters derived from behavior or symptoms, can we use that to explain what happens in biology or to predict some future outcome? And this is where we're starting to say, are they useful? Do they map onto biology? But I would like to argue that we're still a long way from being able to make claims like we can in many other areas of medicine about identifying different pathophysiological mechanisms. The next thing I'd like to point out is that when we use biological data on these kinds of unsupervised algorithms, we have many axes of variance within the data. So supposing I'm illustrating here neuroimaging data, but what I say in the next couple of minutes applies equally to things like genetics, blood-based biomarkers, etc. So supposing we're using this kind of biological data to derive putative subtypes, we might take our favorite neuroimaging derived measure, aggregate it into a data matrix, and then if we were going to do something really simple, like for example principal component analysis, we might end up with some kind of spectrum like this, which shows the explained variance by subsequent components across the decomposition. So it's very likely that we're going to end up in a real clinical cohort with something like this, where we have a lot of variance explained by nuisance effects, for example scanner effects. A bit further down the eigenspectrum we might see something like age and gender explaining variance, because those are quite large signals in the data. And way down here we might get to something that might be clinically interesting. And so that's part of the art behind applying these kinds of methods, is encouraging or constraining the algorithms that we apply to find interesting variation. Another potential problem is that we have, because of these multiple axes of variance, it's possible that we have functional overlap. So suppose we have a putative developmental trajectory for cortical thickness, for example, and we have an interaction between the disease, the pathophysiological mechanism, and the underlying developmental trajectory. If we just train a clustering algorithm without taking account of that developmental trajectory, we're going to get something that's a mixture of lots of different effects. I would like to illustrate this point with a very beautiful slide that was provided to me by Johnny O'Murherty from King's College London. And this shows, what I'm about to show you is the developmental trajectory, a normative model of the developmental trajectory of infants that were born preterm. So these are the brain changes in the first few weeks of life. And you can see that the changes, of course, in this part of the lifespan are very dramatic. But it doesn't matter which part of the lifespan that we consider. The magnitude of any kind of disorder-related variation will be superimposed on variation of a much larger magnitude. So it's really important for us to find methods to be able to constrain the unsupervised or supervised methods that we use to latch on to the right kind of variation. So, some recommendations. How are we going to move forward? I would argue that it's really important for us to be able to use, as I've said a couple of times, to encourage the models that we choose to focus on the most important aspects of variation, not just the biggest, because if we do that, then we end up, if we just do something like apply clustering algorithms to the data directly, what we end up with is a very expensive artifact detector. So one of the things that we can do is we can take account of longitudinal information, so that is in terms of the clinical variables that we use, or in terms of the neurobiology, if that is available. So that will enable us to hone in a little bit on the most important areas of axis of variation. This is something that Christos is going to introduce. So another approach is we can take account of different aspects of neuroanatomy. So we can think about using explicit models of transforming the clinical data into using transformation matrices to constrain the clustering algorithm to try to identify the relevant neuroanatomical changes. Another particularly popular approach is to estimate supervised mappings between brain and behavior. So, for example, canonical correlation analysis is very popular. And this would be in a multivariate setting. So if we have multivariate data, both in the sense of the neurobiology and in terms of the symptoms. One potential problem with this approach is that it's a model that's very prone to overfitting. And this was something that is again showed in the paper, the paper that you can come and visit our poster. And this is an example of canonical correlation analysis estimating a mapping between brain and behavior, so connectivity matrices and symptoms. And you can see down at the bottom on the left-hand side, we explain nearly all of the variance in the data. But under permutation, when we explicitly destroy the information in the data, you can see that the null distribution is centered at about 99. So effectively, the model we have to be very cautious about overfitting when we're using these flexible models. A slightly different approach, which is something that we work on quite a lot in our lab, is to use something like a normative modeling approach to try to explicitly model these underlying sources of variation. And this can be thought of as a generalization of growth charting approaches, where we have estimator mapping, for example, between different lifespan stages and a quantitative biological readout, for example, cortical thickness. But we can also generalize this approach to estimating mappings between brain and behavior. So, for example, estimating a mapping between reward sensitivity and reward-related brain activity. And the point of this approach is that we estimate centiles of variation across the population, such that we can then, for each individual subject, derive a statistical measure of deviation from the expected pattern. Now, this approach has a number of benefits. One of them is that we can, rather than considering the variation across the whole range, we can really focus in on what is relevant for a particular lifespan or a particular point along the curve. It provides us with a way to scale diverse data to population norms. So we express each measure in terms of a Z statistic, for example, that describes the number of standard deviations away from the population norm. And it allows us to accommodate, to a certain degree, the functional overlap between different axes of variation in the data. So, some further recommendations. So this could be used, we could use these kind of techniques, for example, CCA, normative modeling, etc., as pre-processing mechanisms for clustering. But we could also take a step back and say, well, is clustering really the right technique that for what we want to achieve? Could we achieve something similar with a continuous model? And even if there are really clearly defined clusters in the data, which is probably unlikely, we can still explain variation and still make the predictions that we want to make from the data. Another approach is we can think about shifting away from clustering entirely to different kinds of latent variable models, something similar to factor analysis, where we could define a set of, for example, risk signatures. So we have a latent space in which we identify combinations of variables that are associated with risk. And we allow the prediction of individual risk profiles. So the advantage of this approach is it allows the expression of multiple risk profiles within each individual. So we can say, rather than this individual belongs to subtype A or subtype B, it's more of a soft assignment in the sense that we have multiple profiles can be expressed to different degrees in the same individuals. And this provides a way for us to accommodate different overlapping pathophysiological pathways across different individuals. So just to summarize, I've tried to convince you that, I've shown you that despite a lot of hype, there is a huge literature in clustering in psychiatry, and it hasn't really gotten us very far today. And I would argue that it's partially because many of the problems that I've shown you, many studies not testing the generalizability, being satisfied with only a low degree of validation, and not testing against the null data, the null hypothesis that there aren't in fact any clusters in the data at all. I'm not saying that clustering is the wrong thing to do. Used properly, it is clearly a very, very useful tool. I think a healthy way to consider this kind of approach is as a hypothesis generation mechanism. So since we always get clusters from the data, the work then starts is to then demonstrate that these things have really, the clusters that we derive have some kind of biological meaning, or that help us to explain variation that we can't just by taking the diagnostic labels, for example. I would just like to thank the many people who have contributed to this kind of discussion and have contributed to the work that I've shown you today. I'd like to thank yourselves for your attention and invite you to come and visit some of the abstracts. And I'd also invite you to come and visit the Symposium tomorrow, where Koen Haak and Christian Beckman will be discussing this notion of functional heterogeneity in a bit more detail. Thank you very much.